pointed out, as Mr. Nikhil pointed out, we are going to try and learn the basics of Python programming, but using geology. So we can directly apply everything to geology. And so for the actual course, where you will be given data, you will be getting the codes, you will get models and 3D visualization tools, this and the other. The purpose is not to teach programming for the sake of teaching programming, because I realize and I understand that all of you have a background in geoscience and you are interested in knowing how you can apply the basic concepts of programming to get your work done. And that might involve, taking in some data from an Excel sheet or a text file, and then doing some analysis on them and generating some plots, which is typically what you do in Excel. And obviously your question would be, why would I want to do it in Python? I can already do it in Excel. And I'll obviously discuss the advantages and of why we should be using Python instead of Excel. And then I will introduce you to some powerful 3D visualization and 2D visualization libraries, such that you can actually take in some data and do geological modeling. And obviously, we'll go into much more details during the course. During the demonstration, I'll kind of fly through and show you very quickly some outputs to kind of show you the capability that Python has. And then during the course, we will go from scratch. We'll literally start from that. We'll start from the very basics of Python, assuming you know nothing of Python. And then we will gradually, step by step, walk you through how we can do different kinds of things. Now, again, I'm presuming some of you may have had some background in Python programming and so on. So you will probably have to be patient with me during the course, because I'm assuming not everybody knows Python programming in great detail. And I have kind of put in some arbitrary boundaries regarding what is going to be there in the course. And by arbitrary, I mean, we will learn all the tricks and trades up till functions for Python programming. We will not be going into object-oriented programming, for the simple reason you don't need that as a geologist who is trying to solve some problem. You don't need object-oriented programming and things like that. But later we might update this course and we will probably add that. So that discussion is there. So that's day one. Day two of this demonstration, which will translate to about 30% of the course, is about statistical analysis of geological data. I think that we are also going to offer, Mr. Nikhil will talk about this probably after today's session, that we are planning on offering a full-blown course on statistics and data analysis, where we really drill down into different kinds of statistical tests and things like that. So tomorrow's demonstration is more geared towards that class. So today, without further ado, I am going to jump in and show you some basics things that we can do, starting from the simple and gradually going towards the complex. All right, so, and because of that, I am not going to explain to you every line of code, because that's what the main course is all about. During the demonstration, you will have to kind of bear with me regarding that. You will. I think you will have access to the video to kind of work with what we cover today. So I'm going to start very simply with writing a very simple code regarding temperature conversion. And what I'm going to do is I'm just going to paste some code over here that I have already prepared. And the idea is to convert things by temperature in centigrade to temperature in Kelvin. And what I'm going to do is to run this particular cell. There are many ways of doing that, but today I'll use the simplest version. I'll just run that cell, and lo and behold, we can write some little expression that we can use to kind of convert everything into the necessary temperature scale. All right. Now you would say, well, that is pretty simple. We are, that's good thing to know, but what about something much more complex? Well, let's look at looking at stress, particularly for geologists who are interested in structural geology and tectonics, that kind of thing, where we are going to look at some basic ideas of calculating normal stress and shear stress. All right. Now, the background of this is we are going to use a vector decomposition. It's a fancy word, but we are going to use some basic trigonometry to kind of calculate how we can decompose a stress vector into its normal and shear components. So we will use a particular external library called math, and we can use, there are some commands in that library, which again, I'll walk you through some of them, and we can use that to kind of solve some problems. So one of the problems that I'd like to solve is that I want to ask for the stress vector's magnitude and the angle it makes with a particular direction, perhaps. Okay. Now, to solve that, we have to convert things to radians. Remember, a computer doesn't like working with degrees of angle, but it prefers radians. But as humans, we like degrees. So there is a way we can do that. All right. Now, again, if I run this particular cell, it's asking me for the magnitude of stress in Newton per meter squared. Okay. So let me say I put in the magnitude. Where did it go? Did it not run? Yeah. Oh, wait. So it became markdown. That's why. So not pending input. Okay. Let me just stop the kernel. Run that. Okay. So for some reason, let me do something. I have to change something, I guess. I will switch this on real quick. Actually, okay. So what we will do is actually go to that particular code right here. It's here. And, if I enter these values, which if I run this cell, I should be able to. Some problem that's happening, I think, but Why is it searching for history? Should not look at history. Okay, so now it's accepting. All right. So let's say I put in a value of my choice, then it asks for, a different thing. So it wants to know the acute angle between the stress vector and the given plane on which the stress is acting in degrees. And let's say I put in 60 degrees. And then what it will do is it will essentially generate the solution for you. The way I have written the code is it's using what is called F string, and you can actually write it as a human readable sentence instead of just two numbers being spit out. So you can see it says that for a stress vector with magnitude such and such, making an angle of 60 degrees, the normal stress is 86.603 and the shear stress is 50 Newton per meter squared. So you can actually generate solutions that you can understand, and you can essentially copy it and put it as a solution to the problem you are trying to answer. The next thing that I want to show you is essentially if I want to kind of do something repetitively. And to do something repetitively, we use what is called loops. And there are two types of loop, the for loop and the while loop. What is the difference? The difference is in a for loop, we use there is a limit. You put in a limit, like a numerical limit, like I'm going to go from this number to this number, and you have to go over this particular code that many times. And in a while loop, the limit is a condition. So there is a difference between the for and while loop. And although the for loop is much more shorter, crisper, and faster, there are times where you have to use the while loop because you are kind of checking whether a certain condition has been met. So I kind of am going to show you the for example only because I don't need to do everything. So it's the same program. Essentially, what I'm trying to show you is I have the stress magnitude, and I want to show what is the shear stress and normal stress on each plane. So what I have done here, if you follow along, that I have imported this math library. Then I'm going to ask the user for a stress magnitude. Then I'm putting in my variable angle as 90 such that I can put in the limit. And then I'm essentially running a for loop where I am going from 0 degrees to 90 plus 1, 91. Now, you would say, well, why are we bothered about 91 degrees? Typically in geology, we are interested in the acute angle. So we typically stay within 90 degrees, and 90 degree is the limit. Well, it turns out that Python has this weird behavior that it stops when it gets to the last element, but it doesn't execute it. So to beat that, we have to do that so that we can get all the values for the 90 different angles. And so, if I run this cell, I'll do the exact same thing. I'm going to say 100, and it will essentially generate all these values. So it will generate all the normal stresses and shear stresses for you. And again, during the actual course, I will show you that how we can, save all of this into a spreadsheet or a text file that you can import it into a spreadsheet as a CSV file, kind of play around and make it look like a nice table and put it into your report or, whatever that it is you are doing. Let's see. Let's see what else I want to show you. because I don't want to show you simply just this kind of stuff and kind of bore you to death. So what I'll do is I will now switch over to some other code. And so I'll have to, I'll do a new share in a second. And over there, I'll show you some different things. However, I might have to start my thing again one more time. So 1 second. You don't keep the video going. This shouldn't take me more than a second. Okay. So in this particular one, what I want to show you is I'm just going to go to downloads and create. This is where I want, I kind of showed you some mathematical applications. What I want to show you now is what you can do with if you have data and generate some 3D models. So I'm going to create another notebook here. And I'll give it a name in a second once it shows up. Sure. And I'm going to give it model. So I'll give it a. Okay. So in this particular one, we are going to use a fancy library called GemPy, which actually allows us to kind of use kriging data, okay, or generate 3D models. So I'll show you the simplest one first. Again, we'll go into the nitty-gritties and the details of all of this during the course. But we have essentially taken some data which have nothing other than that is taken from an Excel sheet. So I'm showing you this here. So we are going to enter some Excel spreadsheet that has orientations of rock layers, and it has model surface points in CSV file. Now you would say, well, what are these model one underscore orientation.csv? What does it contain? Well, what it contains is a bunch of XYZ data where each XYZ data represents a three-dimensional point. And over here, what I have done is essentially plot the XZ plane with the data. And so what is the data? So if you look at these triangles or arrows, these arrows represent data that is taken from this orientation.csv. And what is this orientation? What does it contain? That CSV file? It will contain XYZ data and the pole to the orientation of the plane. Okay, again, I repeat, pole to the orientation of the plane. That is what you need. You don't need the orientation of the plane. You need the pole. And so here we'll particularly stay with planes. We'll not dive into lines over here. But in the future, we might look into that because the line in 3 dimensions might not have any significance unless you are looking at an ore body. Okay. So these two vectors are essentially showing you which is my right side up. Okay. And if it's an overturned fold, we have to again be very careful as to how we show it. Okay. And I'll show you an example during the course, not here. But here I'm showing some simple examples. So if I can generate the plot for X and Z plane, and you would say, how do I decide that? Well, I have decided it over here. So in the plotting system, I'm showing you that this is the direction. It's going to be a direction perpendicular to the y-axis. And the data that will be plotted is going to be in the X direction and in the Y direction. Okay. And so this is the data that is generated. Now, now I will put in some colors and kind of indicate where the rock boundaries are. Now you see that these points, albeit being in rock 2, see this is the legend over here, rock 2, but the data itself is just on the contact between the two of them, okay? And this the library understands that we have given the data which is just at the boundary, but the rock type of that data is going to be on the layer that is sitting above, okay? Because I have to provide a rock value or a rock type value. Now, in the Excel file, when we discuss that during the actual course, you don't need to write rock 1, rock 2. You can actually put in the lithology name, okay? And obviously, you get a scale bar that kind of tells you the different rock types are shown here. And on the other side, you have data in meters. Or in other words, this data, that the data I have given you, well, the data I have used is actually a 1,000 meter by 1,000 meter by 1,000 meter. Now, I say meter to give you geological concept. The computer doesn't care if you use meter, kilometers, or whatever, okay? All it needs is an array in 3 dimensions to generate the cube. Now, you can create asymmetric cubes or cuboids, which is perfectly fine. And then once it has generated this, well, essentially you are looking at the same thing in different orientations. So this is the X direction. And so I'm plotting here Y and Z. And then I'm plotting X and Z, XZ, YZ. So those are the 2 things that I'm plotting. Now, if I wanted to plot the flat surface, all you would see, the map view essentially, all you would see, it would be one rock, that is rock 2. Or in other words, you have successfully generated a cross-section across a horizontally stratified set of rocks, okay? And yes, this kind of looks, there is a lot of things going on, but when I walk you through, you will quickly find out that this is nothing super fancy. This is something easily that you can handle. Now, let's look at another model where I actually generate a fold. Okay, again, we have the same thing. We have some orientation data. We have some surface points data. Again, I kind of do some computation to generate the model. And then again, I'm saying I want to create a 2D plot. So the first one is a 2D plot of the date of the model in the along the Y direction. So the Y direction is going to be perpendicular to your screen. And so in this particular one, you are just plotting the basic data. See, the geodata is the variable in which all the data has been read into. So this is that geodata in which all the data has been read into. Now, post all kind of calculations, this one is showing the position of those data points. So again, I have 2 arrows that indicate that which direction is the pole to the plane pointing towards. Okay. So it's always a vector. So if it's an overturned vector, then the vector will be pointing downwards. Okay. Or rather the dipping plane. It's the vector of the dipping plane. And so you will, I'll show you during the course how to handle overturned beds. So again, I have just the data. And now I want to see that cross section. So first cross section is perpendicular to the Y direction. So you can see that I have a nice looking fold over here. And then I look at the X direction. And you would say, well, but where is the fold? Well, there is no fold there because you are looking at an X direction. What is the X direction? So the X direction is perpendicular to you. That means if I rotate this figure 90 degrees towards you, so X is perpendicular to the screen, all you are seeing is the bottom of the cube. Okay. And in the bottom of the cube, all you are going to see is just one view, one raw. Okay. But you would say, well, I can see the boundary. So essentially the system is kind of trying to show you where these layers would be. Okay. Now, it would be better if we could show a three-dimensional model of this, because that is a lot easier to work with. So let me show you a three-dimensional model. Okay. All right. Same thing. I have, again, in this one, I have some orientation data and some surface points. And then what I have done is plotted up my data, and you will see that from the legend, you will figure out that this is a faulted block. Okay. Again, this section you are looking at is perpendicular to the y direction, or you are looking at the XZ section, which is parallel to the strike of the fault. Because, you know, that's where you will see the major displacement if the net slip vector is parallel to the is down dip. All right. Now, if it is oblique, then we have to generate a 3D model and kind of rotate it around. Okay. But you can get an idea. So then I want to generate the data to kind of show you how the fault actually works. Okay. And you can sort of see, and these are kind of discrepancies that you will see, but this is what is necessary for the software. You will see that there is this line that kind of comes along, because it is trying to find out, okay, where is this point on the other side of the fault? Because the fault is kind of acting as a barrier. Okay. So it needs to find the other end. And, you know, because of the pixel size or the pixelation, you are kind of seeing edges. So this is an edge effect. And there are smoothing techniques, but again, I'm not going to get into that right now. Okay. Again, all of this can be changed with appropriate values in the Excel spreadsheet. Okay. Similarly, I look at a direction, the YZ direction, and I don't think I show the 3D model, but let me show you that. So, okay. So for that, I need to add some, not there. That's fine. Then add it after this one. So for that, let me grab the code. And this will take a bit of time. So, you know, you will have to, because there's a lot of calculation that would happen during this. So you will have to give me a little bit of time to kind of be able to see the fault stuff. Let's see, where did I put that? So I'm going to put in some code here in pieces. So I'm going to, but this will take a bit of time to load. So let's actually work on this one first. So however far I have written. Okay. So there is a model, example model that I already kind of put in here, and I'm going to execute this. You will have to give me some time. So the star kind of tells us that we need to wait a little bit to compute and download this material. So it's downloading the data, saying that's all done. So I'm going to run this one more time to kind of ensure that everything is all okay. Again, this software takes a bit of time. I have the other part to generate the 3D plot ready, so that once this is done, because this it takes a while to generate the 3D model. So I also wanted to show you that it's not just you press a button and suddenly everything appears, because it's actually computing the whole thing from scratch. Maybe I'll stop this and kind of start again. That cell. It's taking a bit of time, but why don't I show you what it looks like anyways? Okay, so I have to run everything from scratch. Okay, I'll essentially close these then. It's taking too much time. I'll just cells. I really wish I can. This is actually really neat once it shows up. Well, while it's working, what I can also do is show you how we can use some data set. I'll keep an eye on this. This is running. so so as to not waste time, I'll go over and show you how we can do some other kinds of work as well. So over here, I have a data. Oh, no, not in this. I have to show this in, I don't need to do that. I just need to use, okay. So over here, we have some Excel data, and this Excel data essentially contains some volcanic data, or in other words, chemical analysis of volcanic data. And so I have kind of run them to kind of show you the kind of plots we can generate. So this is cerium versus, lanthanum versus cerium. The figures are kind of overlapping for some reason. But that's all the data that shows up. And then I can generate a regression line. In this particular case, I'm using the linear regression parameter. And we are using a particular library called scipy.stats. So this would be one of the things that we will cover in the introductory geology and Python course, to kind of give you a taste of how we can perform simple linear regression using some statistical data or geological data rather. And so what you have here is that, and then we can generate this linear regression line. And from there, we can also calculate the equation of the line. So you actually know the equations as well. Okay. And then just to show you two different kinds of plots, you can have one that looks that has a very good R-square value, whereas the other one has a pretty bad R-square value. So, this tells you there is no linear relation between the data for uranium and scandium. Now, the most powerful thing that is available in these kinds of codes is that you might have 40, 50 elements that have been analyzed, all right? And in Excel, you would be generating those images one at a time, all right? So, and every time there is a new project, you have all these 50 data to repeatedly plot over and over and over again. But if your data format is the same, this one code, obviously we'll have to write, generate the plots for the other things, which can be done through a loop. And you can generate all the 50 elements as a pair in all combinations in just some 15, 20 lines of code. All right. So that is the kind of thing we will be mainly focusing on, how we can accelerate your analysis so that you can spend most of your time looking at the analysis instead of in interpretation, instead of doing mathematics and typing, obscure commands. All right. So that is what the plan is for today. The last thing that I want to show you before I hand over things to Mr. Nikhil is, we can also do modeling without data, like theoretical models. So I am going to show you 3 different plots that essentially is telling us, so this particular program is devised to generate what are the different densities at different depths in the earth, okay? And we are going to use the PREM model, which is essentially telling us the different densities and at different levels. How do we know that? Well, there are, if you look up PREM model of Earth on the internet, you will get the data where we are providing, so we are writing a function over here to generate the densities. So how are we generating the densities? From the PREM model, I know what is the thickness of the core, rather the inner core, and what is the density of, rather, what is the different, these are the two different densities at the top and bottom of the inner core. And this is the thickness of the inner core. The thickness of the outer core is that much, that many kilometers. Obviously, we are working with kilometers here. And the density at the top of the outer core is 9,900 kilograms per meter cube. And the inner one is 12,200, and so on. So then we look at the lower mantle, upper mantle, oceanic crust, and all of that. The crust. We are not making a distinction between oceanic and continental. However, in your model, you could. And what we are doing here is essentially generating an array with the different values of this density spread over this radius. Now, you would say, how is it doing that? What it is doing is, for every kilometer of change, it is preparing a value of density between these two range for the inner core. Or in other words, it's linearly spacing out this density range over this distance. Okay. And this is what it looks like. So if I plot this up, this tells you distance from the Earth's center. So center is at 0 in the x-axis, and this is the top of the surface of the Earth. All right. And this is how the density is varying. So obviously, since this is the center of the Earth, the density is maximum. And you can see the different steps it takes to kind of reach that. Now, how is this steps defined? The steps are defined by your code, your data range. And how did I know that it is linearly spacing out these two density limits over this distance? Because all of these are straight lines. Now I can calculate the distribution of acceleration due to gravity. Now, that has a mathematical equation that involves integration. I'm not going to make you do integrations in the course, but I try to show you how we use numerical methods to kind of solve these kinds of integration problems. So this y int equal to traps y comma r1 is a fancy way of saying I am using the trapezium method, or like, as you know, the area under the, I'm calculating the area under the curve by using thin strips of rectangles, and its numerical equivalent is this command to generate the gravity model. Okay. And then we are essentially, we can plot the gravity model. Again, this is the center distance from the center of the Earth. Obviously, acceleration due to gravity at the center of the Earth is 0. I'm sure you all know that. And at the surface of the Earth, you get around 9.8 meters per second square. So again, same idea. So this is how the acceleration due to gravity is changing with depth. Okay. So therefore, if I can calculate the density profile and the theoretical acceleration due to gravity profile, I can also generate the pressure profile. All right. Now, again, this is a depth z from the Earth's surface. So I've kind of flipped the direction. So this is the surface of the Earth, and you're going towards the center of the Earth. And as you can see, pressure is increasing as you are going towards the center of the Earth. And oftentimes people kind of have this notion, well, acceleration due to gravity is changing, and so the pressure will decrease. Well, actually, the limiting factor for what is the pressure is an interplay between the density and the acceleration due to gravity, and obviously the depth. All right, because the density controls the mass that is sitting on top of a certain point. So this is an example of how you can essentially run a theoretical model with some data and kind of apply numerical techniques to kind of generate plots like this. Well, unfortunately, our friend, the 3D model is still chugging along, generating the model. Okay, it has not yet completed computation of this model. This is fine. It's supposed to do that, but I wish this didn't take this much time. All right. So these are the different kinds of things that we can do with Python to kind of save time for ourselves to solve some geological model-based problem. All right. I'll hand it over to Neil. So this is the three-dimensional model that has been generated, and you can actually rotate this. So what we have over here, and you can actually see it has generated, oops, sorry. See, this is the other thing. I messed things up once. So this is your view angle. And so it has, I've given rock names like gneiss, schist, sandstone, two, shale, siltstone, and so on and so forth. And then I have generated, like this is essentially a graben you are looking at. So you can actually see how this one layer comes in and gets, the cutoff is here, and the other cutoff is, now this is the error part. So this cutoff, and this is where you have to play with the data. I did a quick model here that you can see that the green surface kind of starts over here. It shouldn't do that, because that otherwise there is no displacement. It seems that this is folding. That is not the case. This layer needs to come over here, but the software cannot do that very easily, because the first thing it does is once it plots the faults, it traces where my layer is going. And that is why it gives you these continuous curves. So during your interpretation, you have to take this model into either ParaView or understand that the displacement is actually this green layer is going to intersect either here somewhere, and therefore that is the displacement. All right. And that's happening for each of them. This purple layer is also there, this blue layer is also there, and so on and so forth. And then you can turn it around in any direction you want, and you can see the vector data that tells you the normal to the plane are also shown. All right. And in these kinds of problems, particularly, we keep multiple vector points. So you can see that this is the vector point for the red layer on the left side of this fault, but there is these vectors of the red layer pointing towards each other, so that this fault has kind of been folded, or that there is a sag in the layer is kind of represented. Okay, now these are computed vectors, so that might be an issue, and this is also superimposed on the vector for the faults as well. But the main fault plane in the graben is this vector showing the top up. Okay. Again, we'll talk about this in details during the course, and why we need all these vectors and so on and so forth. But you can see all I need is 2 Excel files with your geological model, and I can generate these in 3 dimensions. And all I have to do is run the code and wait a few seconds. The model actually doesn't, actually the model, see this, there is 2 lines over here. There is 4 lines over here. There is 2 lines, so 4 to 6 to 8. And then this is essentially 1 line. I have kind of divided it into these different parts. So all I essentially have is 8 to 9 lines of code, and maybe wait for 5 minutes or something like that you did wait. And lo and behold, you have a geological model that is faster than anything that you can generate on your own. Yes, the course is for the workshop for today and tomorrow is for geology course in June. Well, part of tomorrow is for another course that we are thinking, which is detailed statistical analysis. That's all I have to show for today.